Okay, so I'm going to talk towards the future of AI. This will be a little bit of vision, but particularly in the context of self-supervised learning. Mute. All right, I'm muted. So first of all, there's a lot of noise these days, particularly in Silicon Valley, about superintelligence, and there's sort of wide kind of variation of estimate about how long is it going to take for AI to kind of become as smart as humans. Some of the more exotic people think it's going to take maybe a year or two. They will have like PhD level intelligence within a year or two. I don't believe this at all. It's going to take a while. We're missing some essential component and breakthroughs for this. And those have to do with vision, actually sensory input, as we'll see in a bit. But then we might ask ourselves the question, like, why do we want to get machine as intelligent as humans? And we'd like machines to basically amplify human intelligence, and we'll need to interact with them. And the most convenient way to interact with machines is if machines are like humans, because we're used to interacting with other humans. And so we need a human-level AI assistant if you want to build a human-level intelligence, if you want to build AI assistants that are with us at all times, help us in our daily lives, and would be as if we were kind of working around with sort of a staff of smart people working for us, except there wouldn't be people. But the future is one in which, maybe distant future, is one in which all of us basically be the boss of a staff of intelligent entities working for us. We need that intelligence to be human-like because we are familiar with interacting with human intelligence. So at Meta, there is this whole idea that smart assistants will live in wearable devices such as smart glasses. I'm actually wearing smart glasses here. And if you smile, you'll be in the picture. Okay. I actually gotten used to, the problem with this is that I'm not in the picture, so I've gotten used to actually taking selfies of myself really fast. All right. Okay. So there will be, smart glasses that we interact with through bracelet that measure our myoelectric currents and things like this, so we can point and click, or even type with our hands in our pocket. This is coming actually pretty soon. But there's an issue with sort of building human-level intelligence, which is that current AI technology is nowhere near where we need it to be. In fact, it really sucks compared to what we see in humans and animals. The learning abilities of machines are really not that great. So we moved over the last few years from supervised learning to reinforcement learning to now self-supervised learning, which really has revolutionized AI over the last few years. But the type of self-supervised learning that we use at the moment in the context of large language models, for example, is very limited. It only works for training with a sequence of discrete symbols, essentially. There's another issue, which is that most of the AI systems that people are familiar with basically perform inference by forward propagation through a fixed number of layers. And that includes LLMs, by the way. And that's computationally very limited. So I'll propose some alternative to this. And generative prediction, as I just mentioned, only works with really discrete symbol sequences. It doesn't really work if we want to train a system to learn how the world works by observing to vision, for example. And autoregressive prediction is really not a good way to kind of represent the type of thinking and reasoning that humans and animals are capable of. So humans and animals have mental models of the world that they can use to kind of imagine the consequences of their actions and plan actions. Their behavior is driven by objectives. that need to be fulfilled, or sub-goals that we set for ourselves. And of course, we can reason and plan complex action sequences. And even animals are capable of doing this. We don't give them enough credit for how smart they are. So we need systems that learn well models from sensory inputs, like vision, but other modalities as well. We need systems that have persistent memory, that can plan action sequences so as to fulfill a particular objective. And systems that can reason. Planning and reasoning really are the same thing. And systems that are controllable and safe. So the first question we might ask is, what type of learning is taking place in humans and animals? And it's obviously, a lot of it is purely by observation. There's a lot by interaction as well, but before 3 or 4 months, babies hardly can influence the world. They can mostly just observe, and they accumulate a huge amount of background knowledge about how the world works. So this is a chart put together by my friend and colleague, Emmanuel Dupuy, who is a developmental psychologist and cognitive scientist. They say, think basic concepts like object permanence pop up in human babies around 2 months. Things like babies being able to kind of attribute categories to objects. They don't give names to them, but they know that the table and the chair are different things. That pops up around 4 or 5 months and then continues for quite a while. But then concepts like intuitive physics, gravity, inertia, conservation of momentum, this kind of stuff, that only pops up around 9 months or so. It takes 9 months for babies to really kind of integrate the fact that objects are supposed to fall. So if you show the scenario here at the bottom, where a card is on a platform and you push the card off the platform and it appears to float in the air, 6-month-old baby will barely pay attention. And then 10-month-old baby will go like the little girl here, be really surprised because by then, she's learned that objects are supposed to fall. It's a trick, obviously. So what kind of learning is taking place when babies are capable of doing this? And animals for that matter. And so we can ask ourselves, a question that's related to this, which is, why do we have systems that can pass the bar exam, solve equations, compute integrals, solve math problems, but we still don't have domestic robots? We still don't have even robots that are nearly as agile as a cat in terms of planning abilities. We still don't have, household robots that can accomplish any task that a 10-year-old can accomplish the first time you ask the 10-year-old, if you can convince the 10-year-old to do it. We have millions of hours of training data of cars being driven by people that we can use to train a neural net to drive like humans. It doesn't work. We still don't have level 5 self-driving cars. Yet any 17-year-old can learn to drive a car in about 10 or 20 hours of practice, largely without causing any accident most of the time. So, obviously we're kind of missing something big that, as it turns out, and this is Moravec paradox. So Moravec is a roboticist who said many years ago that, how come we can get computers to solve super complicated problems, like playing chess, better than humans, but we still don't have robots that can, just navigate and grab an object properly. I mean, now we're starting, but it's very ad hoc. So we're missing something big in terms of the architecture of our AI systems. And there is a bit of a delusion in the fact that, LLMs and chatbots can manipulate language, and we get fooled into thinking they are smart because they can manipulate language, but it's just an illusion. And look at those numbers. So a typical LLM is trained on the order of 30 trillion tokens. A token is like a word or like a subword unit. And a token is typically 3 bytes. And so that corresponds to about 10 to the 14 bytes total data to train the biggest LLM. It would take 400,000 years, maybe 500,000 years for a human to read through that. Whereas a human child has been awake a total of 16,000 hours in the first 4 years of life, which, by the way, is a small amount of video. It's only about 30 minutes of YouTube uploads. You guys probably know better than me that we have about 2 million optical nerve fibers going to our brain, each carrying roughly about 1 byte per second. It's an order of magnitude. And though if you do the arithmetics, you get to about 10 to the 14 bytes in 4 years. So there is way more data getting to our brain through the visual cortex than there will ever be through speech and language. It's much denser. It's also more redundant. And so you would think that there is less information because it's more redundant. But in fact, if you want a system to be able to learn anything about the structure of the data needs to be redundant. If there is no redundancy in training data, you cannot use machine learning to do anything with that data. Okay? Machine learning thrives on redundancy. So that tells you we're never going to get to human-level AI by just training on text, first of all. And second of all, that we need to be able to kind of basically discover techniques to train a system to learn from video. But before I talk about that, there's another issue, which is inference. So as I said, neural nets, LLMs, and convolutional nets, and all those things perform inference by propagating signals through a fixed number of layers of a neural net and then produce an output. In the case of large language models, they do this multiple times. Every time you propagate through the fixed number of layers, you produce a token, and then that token gets injected into the input and then produce the next token, etc. But it's still propagation through a fixed number of layers. But there is a better way to perform inference in a slightly more conceptually more refined system, and it's based on the idea of optimization. Normal you can see it, great. Okay, so normal inference through perception, vision, for example, you propagate through a fixed number of layers. Let's say the equivalent in human would be fast perception through the ventral pathway, from the retina and lateral geniculate nucleus all the way to the infratemporal cortex, and produce an output. This only works for like fast reactive vision, on the order of 100 to 200 milliseconds in humans, because in reality, the human visual system is not feed-forward. It's more complicated. It's got recurrences and things like that. If you look at something for longer, you might kind of discover something about it that you didn't see with just a glance. But really, the sort of more general way of viewing inference is as a process of optimization. So essentially, you're looking at an observation from the world, run this through some perception module that produces a representation of the first set. And then there would be some other neural net, learning machine, whatever you want, who has a bunch of inputs and a single scalar output, which is not represented here. It's sort of implicit. Whenever I use this rectangle symbol, that means there is an objective function that produces a scalar output. And the role of this scalar output is to basically measure the degree of compatibility between the input and a proposed output. Okay, so I show a picture of an elephant. I put the label elephant, and the output should be, let's say, 0. And if I put the label of something else, let's say a table, then the scalar output of this objective should be larger, okay, than 0. Now, what that means is that by optimization, if I have a particular observation, if I search among the set of possible outputs for one output that minimizes this objective, then I perform inference. Okay, the advantage of doing this is that it's computationally strictly more powerful than just feed-forward propagation through a bunch of layers. There's more functions you can implement efficiently this way than you could this way. You can reduce basically any computational process to a process of optimization or search. Okay, in fact, this is very classical in traditional AI, if you want, pre-deep learning. And the other advantage is that this is a good way of representing a dependency between variables where there may not be a single correct output for a given observation. There might be multiple correct interpretations for a particular percept. What you want is all of those interpretations to have low energy. Okay, we're going to call this an energy function. The output of this objective is going to be an energy. And so it's a good way of representing mappings that are and dependencies that are not necessarily functions. And as I said, it's very classical in traditional AI, the fact that things like search planning in classical AI consists in actually looking for an output that best satisfies a set of criteria or objectives. Find the shortest path between a bunch of cities, for example, the traveling salesman problem. Explore the tree of possible moves at chess for one that will lead to victory for you, for example. So path planning, things like that, right? This is all, or SAT problems, logical inference. All those can all be reduced to search. So we need AI systems, whether they're based on deep learning or not. We need them to perform inference by optimization because it's just more powerful. And it also would explain the fact that when we are faced with a complicated problem, we spend more time thinking about it than if we're faced with a simple problem, right? That's because the optimization, the search is more complicated. So LLMs don't do this. LLMs do feed-forward propagation to a fixed number of layers. So given a set of tokens, discrete symbols, you run them through some big neural net, and it produces the next symbol. Okay, and that's a fixed amount of computation. You inject this symbol into the input by shifting everything by one, and then you can use it to predict the second symbol, shift that in, third symbol, etc. Right? So it's called autoregressive prediction. It's not new. It's been around for longer than me. But it's and the way you trick an LLM into thinking about something harder than for a simple problem is that you trick it into producing more tokens. As a result, it's going to spend more computation producing those tokens, right? But that's kind of a hack. And in fact, there is a major issue with autoregressive prediction, which is that every time you produce a token, there is some probability for that token to be wrong. By wrong, I mean that within the tree of all possible token sequences, that particular token takes you outside of the subtree of what you would consider correct answers. And so assuming there is such a probability and that the probability of errors are independent and all the same within the sequence, which is, of course, an approximation, then the probability that the sequence of length n would be correct is 1 minus this probability of error to the power n. So it decreases exponentially. Okay, and there is no way you can do this. You can fix this in the framework of autoregressive prediction. So what a lot of reasoning AI systems do these days, LLMs, is that they generate lots and lots and lots of different token sequences, and then they have a way to select which of those sequences are most likely to be correct using a second neural net that basically evaluates the answers to the first one. Okay, and this is also the way systems like chess players and Go players based on deep learning have worked. You have a first neural net that produces branches in a tree of possible moves that seem likely to be good, and then you have a second neural net that basically evaluates which of those branches are the best. So the reason why LLMs have been so successful, though, is because they're really easy to train, and the training that we use for them is very scalable, right? So this is a kind of a representation of a typical LLM GPT style architecture where you have a transformer, a parameterized function that looks at a window, which may be very large, of input tokens, and for this, it is trained to produce the next token, but the system is trained in parallel at the sequence level. Okay, so you show it a sequence of inputs, and then you just ask it to reproduce the input sequence on its output. So basically, compute the identity function. But the connection is causal, which means that the network cannot look at one particular token to predict that token. It can only look to tokens that are to the left of it. Okay, so it has to basically do prediction to be able to solve the task. But secretly, it's actually an autoencoder, for those of you who know what that is. So that turns out to be efficient and surprisingly powerful, but very limited in many ways. So the way, as I said earlier, humans and animals can build mental models of the world that allows them to kind of predict what's going to happen, predict the consequences of their actions, etc. What is a world model? World model is something that, from, let's say, past observations, let's say a few frames of a video, in the case of a AI system, let's say a robotic system, runs them through some encoder that produces a representation of this. And then that system is capable of predicting the representation of the future state of the world, given the current state of the world and an action that it imagines taking. Okay, so if you have current state of the world, action, prediction about the next state of the world, you have a world model. Now, a world model is very useful because you can use it for planning. You can then use it to imagine what the consequence of a sequence of actions would be. And then you can try to search for a sequence of actions that accomplishes a particular task, right? That's objective-driven system. Okay, so if you want to go in that direction, we might think that we could use the same trick as LLMs, just instead of training a system of this type on text, we could train it on videos, all right? So that would be a generative architecture that we train on video. Take a video, for example, corrupt it, let's say mask the second half of it, run it through an encoder, and then train a decoder to predict the missing part of that video, okay? And then have some sort of cost function that measures the prediction error, right? Train the system to do this. Bad news, it doesn't work. And I've been working at this problem for longer than people have been working with large language models. Been working on this for 15, 20 years. It simply doesn't work. We tried many things. The reason it doesn't work very well is if you ask the system to just make one prediction, since it cannot exactly predict all the details of what's going to happen in the video, because there's just not enough information, it predicts the average of all the possible outcomes, and that ends up being a blurry prediction. This is an old paper, almost 10 years ago now. And you see, you show 4 frames to the system, ask it to predict the next 2 frames, and the predictions are horribly blurry because it predicts the average of all the possible futures. This is another example with kind of simple videos that are like the top-down view of a highway, and you have a car in the center, and the system is meant to predict what the other cars are going to do. And again, if you train a neural net to make that prediction, it's going to predict very blurry mess instead of the proper thing. So with various approaches, like latent variable models, you can mitigate the problem, and those are animations using a particular way of doing this, using latent variable models. But it's expensive and only works for kind of videos like this, or for video games. Doesn't really work for natural video. Nowadays, people are trying to use things like diffusion models for that. And of course, there is a lot of activities on trying to actually produce nice-looking video, which in itself is an interesting problem. But if you are interested in the system understanding how the world works, generating pixels is a complete waste of time. It's just too complicated. I mean, the problem is really impossible. If I take a video of this room and I kind of pan the camera slowly towards the middle of the room, and I stop here and I ask the system to predict the rest of the video, it can predict that there are people sitting in chairs, and this is a meeting room, and there's probably a wall on the back and things like that. But there's no way it can predict what every one of you looks like. There's just not enough information. So it's going to have to either make it up or just produce kind of blurry representations, right? So it took me a while, but the solution to this is an architecture that I've been sort of working on with many of my colleagues, and there's a whole community working on this now. Architecture called JEPA. That means Joint Embedding Predictive Architecture. And if you search for Joint Embedding Predictive Architecture on Google right now, between double quotes, you'll get on the order of 700 hits. So there's a lot of people working on this kind of stuff. And And the basic idea is very simple. Instead of having a generative architecture that would predict every details at the pixel level of the reminder of the video, you encode the video, both the complete video and the partially masked one. You encode them and you perform the prediction in this representation space. Okay, and this is really what a world model is. In a world model, you're not predicting all the details about what goes on in the world. In your head, you never predict all the details of what goes on in the world. You have some abstract representation of what goes on with the kind of relevant piece of information about the state of the world, and you are able to make predictions about that abstract representation, but a lot of details are not predictable by your brain, your visual system. At a very low level, many details are predictable, as many of you know. There is things like illusory contours and stuff like that, right? So neurons kind of fill in the blanks if they feel like they should be looking at something and they don't. They sort of act as if they do. So there's a lot of processes of this type of prediction, essentially, taking place in the visual cortex. But at a high abstract level, you find your visual system and your brain in general finds abstract representation of what you observe and then makes prediction in that abstract representation space. Okay, so the difference between the two architectures is like that. On the left, you have generative architectures predicting every detail. The cost function is a distance in input space. On the right, you have those JEPA architectures, which make prediction in representation space. Now, there is a major issue with the JEPA architecture, which is that you have to be careful that it doesn't collapse. There is, if you train that system, you just train those neural nets to minimize the prediction error. Basically the difference between the representation of Y and the predicted representation of Y. The system can choose to completely ignore X and Y, produce constant representations, Sx and Sy, and now the prediction problem is trivial, and the prediction error is 0 all the time. Okay, but that's not a good solution. So the difficulty with training JEPA is to make sure that it doesn't collapse, it doesn't ignore the input, essentially. And there's two ways to do this. I'll come back to this later, but there's two ways to do this. One way is to make sure that when you show it different inputs, it produces different representations. Okay, those are called contrastive methods. There's another way, which is that you're trying to maximize the quantity of information that is coming out of the encoder, but at the same time minimize the prediction error. So the system will find a trade-off between propagating as much information to the representation as possible about the input, but yet only propagating things that it can predict because it needs to minimize the prediction error. Now, if you think about this type of problem of like observing data and then finding an abstract representation of this data that allows us to make prediction, it's not just our perception system or AI system that are doing this, but it's also what we do in science. In science, we try to find relevant variables and appropriate representations of observational data that allows us to make predictions. So, for example, the trajectory of planets in the sky is super complicated. Planets go back and forth and everything. But if you have the appropriate representation for the position of planets relative to the sun, you know that planets, including the Earth, rotate around the sun. Then those trajectories are very simple. They're just ellipses. Similarly, we know a lot about the planet Jupiter. We know an enormous amount about the planet Jupiter. But if we want to predict where Jupiter is going to be 100 years from now, we only need 6 numbers, 3 positions, 3 velocities, and we're pretty much done. So we never know which representation is going to be useful for a future task. But the point is, learning representations is really key to being able to behave intelligently and have good mental models of the world. In fact, let me dig a little bit in that point here. In principle, there would be a description of everything that takes place in this room right now in terms of quantum field theory. It would be kind of insane, right? Because we would have to measure basically the wave function of this entire room, which is impossible. but also the amount of computation that we would need to do is just, insanely complicated, even with quantum computer. So we invent abstractions that allow us to make predictions. Okay, particles, atoms, molecules, materials, objects, machine in the living world, proteins, organelles, cells, organisms, individuals, societies, ecosystems, right? And so we have this whole hierarchy, and at every level we have, every level we go up, we have a more abstract representation of the process at the bottom, which eliminates a lot of details about what goes on, but allows us to make a longer-term prediction with fewer details. Okay, it's a very fundamental thing, and it's a mystery to some extent why it is the case that our universe is structured in such a way that such hierarchical representations actually allow us to apprehend the world. This famous quote from Albert Einstein, which is one of my favorite one: the most incomprehensible thing about the world is that the world is comprehensible. Okay, so now assuming that we can train a system to kind of learn world models like this that make prediction in representation space, particularly that can predict the state of the world resulting from an action that the agent imagines taking, how are we going to build a system around this world model? So I wrote a position paper on this. It's rather long. It's basically, it's more like a vision paper. It's like my vision in the other sense of the term. It's basically my idea of where AI research should go over the next 10 years. Well, it was 3 years ago, so maybe over the next 7 years now. But it's still up to date. This was published before ChatGPT craze and everything, but hasn't changed. It's on open review, not on archive, so you can make comments if you think it's wrong, or just slightly incorrect. Okay, so here is how you would build an AI system, complete AI systems, if you had a way of training a world model through prediction, as I described earlier. Okay, so make an observation about what you can currently perceive, run this through some perception module that produces some representation of the current percept, combine this perhaps with the content of a memory that contains your idea of the state of the world that you do not currently perceive, right? You probably have some idea about the state of your house or whatever, or your office somewhere. And you might need to combine this with the current percept, or maybe update this memory with your current percept to get an idea of the current state of the world. Now you feed this to the world model, and the world model is also fed with a hypothesized action sequence that is imagined by the agent. So the world model predicts the resulting state of the world that will result from taking this sequence of actions. And then you can feed this to an objective that measures to what extent the task has been accomplished. So that's, again, an objective that would produce a scalar value 0 if the task has been accomplished, and some positive number if it hasn't. Possibly something that indicates to what distance to accomplishment you are from. And perhaps it would be another set of objectives that you could think of as guardrails. So things that, if you ask your domestic robot to go fetch you coffee, and there is someone standing in front of the coffee machine, you don't want your domestic robot to just run over that person or slash into death to get access to the coffee machine, right? So you want some guardrails so that the system sort of behaves properly. We have many such guardrails in our brain, by the way, that evolution is built into us so that we don't systematically kill each other, only occasionally. All right. Okay, so then the process is the system would search for an action sequence that minimizes those objectives. Okay, so it's inference by optimization. And it might be difficult. It might be that there are many things that could happen, and then you have to explore a lot of different actions and things like that. Okay, if everything is differentiable here, you can do this optimization using gradient-based optimization procedure. You can backpropagate gradient through this and then update this using gradient descent. Okay, if you have a world model, you probably have a world model that tells you, given the state of the world and a single action I might take, what is going to be the next state of the world. And what you can do is repeat the application of this world model for multiple actions if you imagine taking a sequence, right? So here is the initial state that you observe from perception, and then you apply your world model here twice for a sequence of 2 actions, apply the guardrail cost to the entire trajectory, and then the cost of the task to kind of the final state, that determines whether the task has been accomplished. Did you open the door? Did you make coffee? Whatever. Now, the world, unfortunately, is not completely deterministic. So, and neural nets are deterministic functions. So, the way you make a deterministic function non-deterministic is that you feed it an extra argument that is a latent variable, a variable you don't know the value of, but you can sample it from distribution, or you can infer its value according to various criteria. Ultimately, what you want to do is something that is basically you want to build a system that is capable of hierarchical planning. So if I want to plan, let's say I'm sitting in my office at NYU and I want to be in Paris tomorrow. I cannot possibly plan my entire trip in terms of the low-level actions that I'm able to take, which are basically muscle actions, right? So muscles have to be controlled, like, every millisecond or 10 milliseconds or something. I cannot plan my trip from my office in New York to Paris in terms of millisecond by millisecond muscle control. For 2 reasons. First, it's computationally infeasible, but second, I don't even have the information. How can I plan my entire trip? Like, I'm going to go down on the street. I don't even know if the street light is going to be red or green. That's going to determine what action I take next, right? So I can't plan too much in advance. But what I can do is plan at a very high level of abstraction. Okay, I can plan that regardless of what goes on. If I want to be in Paris, I have to go to the airport and catch a plane. This is a very high-level description. It only consists of 2 actions. Okay, they are very high-level actions. But I don't need to know much to be able to make this plan, right? Okay, so first action, going to the airport, which means I have a sub-goal now, going to the airport. I have a sub-objective, which is how far I am from the airport. And so distance to the airport is now my sub-goal, right? That I need to optimize with respect to the actions. And again, I can do this at a fairly abstract level. I'm in New York, so I can just go on the street and hail a taxi for the airport. And I have another sub-goal, be my distance to the street, being on the curb. And you can imagine kind of going down this way. Now I have to, the next level down is I need to go to the elevator, push the button, go down and work at the building. How do I go to the elevator? I need to stand up from my chair, pick up my bag, open the door, walk to the elevator, avoiding obstacles on the way, say bye-bye to my students. I'll see you next week, and blah, 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 right? And then at some point, it's slow enough, and I have all the information I need that I can just take the action without actually having to plan. So this problem of hierarchical planning is essentially completely unsolved. And what's unsolved is not the planning itself, it's more the issue of learning a multi-level hierarchical world model that is capable of learning abstract representations of the world to perform this kind of task, right? And humans are particularly good at this, but animals can do this quite well too, at multiple levels of abstraction. So this whole thing put together kind of leads to some sort of architecture for an AI system that would have all the appropriate characteristics. Call this a cognitive architecture. It looks a little bit like the brain organization of many animals, with perception, short-term memory, perhaps similar to the hippocampus. Or one model in our brain probably is somewhere in the prefrontal cortex. And by the way, we probably have only one engine capable of doing predictions this way, which is why we can only accomplish one conscious task at any one time, because we have to reuse the same hardware for like multiple tasks. And probably somewhere in the base of ganglia and other places in the cortex, we have a bunch of objective functions that can be configurable for the situation at hand, and guardrails as well. Inhibition, people call them. Okay, so now we're down to the problem of training a world model from observation, mostly, a little bit from actions as well. That's where self-supervised learning comes in. So I told you about this joint embedding architecture, JEPA, joint embedding predictive architecture, which is here and here. But in fact, the idea of joint embedding, so training a system to learn good representations, so that representations, for example, are similar if the two inputs, if you know that the two inputs are semantically identical, and different if the inputs are different, or architectures that are capable of predicting the representation of a y from the representation of an x. And similarly, with predictors that are conditioned on either actions or latent variables. Okay, so those have like different names. This used to be called Siamese networks when those two networks were identical. There's various methods to prevent collapse in this case. This is the full JEPA, or at least action condition JEPA, etc. And what we're gonna have to figure out is, how do we train those things? Now, in machine learning, one of the preferred way of conceptually understanding the process of training is probabilistic modeling. Okay, you basically model a machine learning system as estimating some sort of distribution. Now, the problem with this is that it works great when what you're predicting is discrete, or when it's continuous and low dimensional, or whether the distribution is relatively simple. But in high dimensional continuous spaces, parameterizing a density function in a high dimensional continuous space is basically intractable mathematically. And so I'm using a formalism that I've been pushing for a number of years called energy-based models. And it's sort of a weakened form of probabilistic modeling, if you want. In fact, probabilistic models are kind of a special case, if you want. And here's how it works. If you want to model the dependency between x and y, you don't necessarily know that there is a functional relationship that allows you to predict y from x, because there could be multiple y's that correspond to a particular x. But if you want to just model the dependency between those two things, let's imagine that the training samples of your machine are those black dots, okay? So there's clearly a very strong dependency between x and y, but there's no functional relation between x and y because there's multiple y's for a given x that have, that are good. So one way to model this dependency is to train a model which produces a scalar energy function, where this energy is 0 if x and y are along basically the manifold of data or high data density, okay? And the energy is higher as you move away from that manifold, okay? So now if I give you a value of x and I ask you what's a good value of y, by optimization, minimization, you can find a good value of y or multiple value of y's in this case that corresponds to that particular x. But it's not a single function. Okay, now we're going to have to train those systems, right? So, figure out what architecture we give to the system, but I already mentioned what it can look like. But then train it so that it gives low energy to stuff, to x and y's that are compatible, and higher energy to everything else. Now, there's two classes of methods for that: contrastive methods and regularized methods. So on the left here, you see an example of an energy function that basically collapses. It doesn't really capture the dependency between x and y. Let's imagine this is x and this is y. It doesn't really capture the dependency between the two because it produces 0 energy for everything, right? This is an instance of the collapse problem that I mentioned earlier. System basically ignores x and y and just produces 0 all the time. Contrastive methods consist in generating those green points, which are outside the manifold of data, and then pushing their energy up. Okay, it's become very popular for a lot of applications. In fact, a lot of image recognition systems that are used in the context of LLMs or for search engine actually use contrastive methods these days. You show is a class of method that people have come to call clip. You show an image, you run it through some neural net, it produces a representation, and you show a text, you run it to some neural net, produces a representation of that text. If the text is a good description of the image, you try to pull those two representations towards each other. Okay, so you train the two encoders so that the representation of the text and the image are similar. And then you show another description of another image, which you know is different from the image you show, and then you push those away. That's an example of contrastive method. But the problem with contrastive method is that if the representation space within which you do the training is high dimensional, the number of contrastive samples you're going to have to generate for the energy surface to take the right shape is going to grow exponentially with the dimension in the limit of an infinitely flexible learning system. So it doesn't scale very well. Regularized methods work by basically minimizing the volume of space that can take low energy, so that whenever you push down the energy of training samples that you observe, energies outside of that has to go up because there is only a small amount of low energy volume to go around. Okay, it seems a little mysterious, but really we have those two classes of methods. I've become a much bigger fan of the second type. This collapse problem, by the way, is very common in sort of various approaches to machine learning. Autoencoders, for example, where you only have a variable y that the system attempts to reconstruct. Those can collapse by basically just running the identity function. That gives a reconstruction error that is 0 everywhere for every y. And what that means is that the system has not captured the internal structure of y. You want an autoencoder to give you 0 energy for things you train it on, but you want it to not reconstruct things you don't train it on, and that's where it becomes complicated. That's why you need to, regularize or train with noisy inputs or use diffusion models and things like that. I said before, energy-based models probabilistic models are basically a special case of energy-based models. You can often transform an energy that captures the dependency between variables into a conditional probability of y given x. Just do e to the minus the energy of x and y, normalized by the sum or integral of the energy for all possible y's. And what you get is something that normalizes to 1 when you integrate over y, and so it's a proper probability distribution over y. When you train an energy-based model, you only get a proper estimate of distribution if you use particular loss functions to train it, called the negative log likelihood. I'm not going to go into the details of this, but there is a connection. But basically, this denominator is almost always intractable. And so why go through the pain of finding approximations to this when you can just manipulate the energy function directly and just not worry about distributions? So I've made a list of, I'm not going to go through all of it, but a list of a bunch of different methods, classical methods, published methods, as to whether they are contrastive or regularized. And I'm not going to go through that. But let me take some concrete examples of how self-supervised learning can be used in the context of JEPA or joint embedding architectures. For example, to learn good representations of images in a completely self-supervised manner. So one way to do this would be, okay, I show two images which are basically transformed versions of each other to an encoder. Maybe those two encoders are identical. And I train the encoder and the predictor to predict the representation of this image from the representation of that image, or vice versa. And if the system is capable of doing this, it probably will have kind of, extracted a good representation that basically captures, what there is to capture about the input. Once you've trained that system, you remove the predictor and you use the representation as input to a simple classifier that you train supervised, and then you measure the performance of that system, of that classifier, whatever it is, on new data. So contrastive methods are very simple. They consist in showing pairs of images that are are semantically identical, and then pulling minimizing the prediction error, basically pulling this next to that. And then showing pairs of images that are different, and then pushing those things away from each other some distance. The early work on this goes back to a paper of mine from the early 90s when I was at Bell Labs to do signature verification. And then some more recent work from my lab at NYU. I mean, it's still 20 years old. And then that interest in this kind of method got revived in the last 5 years or so. But in the end, they don't seem to be the best method. The best methods at the moment are the ones that are based on distillation. So there's a number of different methods. This one is from DeepMind, BYOL. Those are from Meta, from FAIR. And the basic idea of this is that same thing, you take an image, you transform it or corrupt it in some ways. You run this image to an encoder, run this image to another encoder. Those two encoders have to have the same architecture. And again, you train the system overall to predict the representation of Y from X. Now, the trick here is that somehow to prevent collapse, the trick is to not backpropagate gradient to this half of the network and to set the weights of this network as essentially an exponential moving average of the past weights of that network. Okay, so take the past weights of that network and compute a running average of those weights and set the weights of this guy to this running average. So basically this guy, its weight don't change very fast. They kind of smooth out if you want. And they're not updated using gradient descent. And you need to do a little bit of normalization and stuff like that. If you train this system, it's not going to collapse. Why? I don't know. Which is unnerving. There are a couple of theoretical papers that show that with simplifying assumptions about the type of encoders and predictor, if you make them linear, you can show that there are fixed points of the gradient descent dynamics that actually are not collapsed. Okay, it doesn't mean the system is never going to collapse. It means that there are non-collapsed fixed points of the learning dynamics, but it's not really satisfactory, right? I mean, we don't really understand why it works. In fact, it still works if we remove this AMA. If we just copy the weights here, it just doesn't work as well. So there's a lot of mystery around this, but it does work really well. And in fact, those JEPA, VJEPA techniques are really pretty cool to learn image representations in a completely self-supervised manner. There's an example of such method as well called Dino, or Dino, but it's made by French people. They pronounce it Dino. They are at Meta in Paris. And it's very much this. They have a few tricks on how they kind of represent SY. It's basically a very large classification layer here with softmax, and you have kind of a cross entropy between those two things and some normalization and blah, blah, blah. And it doesn't collapse. There's a few tricks. And it works really, really well for learning representations of images. In fact, there is some slightly more recent work earlier this year that showed that if you scale up the Dino network and you scale up the data set you train them on, you get performance that is either the same or better than the best supervised systems that have been trained on those problems. Okay, so there was a big question until the beginning of this year as to whether self-supervised learning will ever surpass supervised learning. And now it's not a question anymore. It's clear that it does. Okay, you just need to scale things up and do it right, obviously. And it's cool because with Dino, you can have like fairly generic representations of images that seem to be applicable to just about anything. In fact, probably the best, and people have used Dino for all kinds of applications in medical imaging, in biological image analysis, in astrophysics, in all kinds of domains. The latest version is called Dino v3, which just came out last month. And again, it shows that basically self-supervised learning now either matches or surpasses the best supervised methods. And you get sort of generic representations of images, basically a generic feature extraction that you can use for all kinds of stuff that essentially produce state-of-the-art performance for all kinds of different visual tasks, whether they are kind of semantic, like object classification, or whether they are things like depth estimation, video tracking, segmentation, and things of that type. So because we're interested in those this kind of planning abilities and world models, did some work. So this is a student of mine, Cassie Zhu. She goes by Cassie. Heng Kai Pan, also a student. Myself and Neural Pinto, who is a colleague at NYU, roboticist, and we co-advise Cassie. And basically what we did was use the Dino V2 encoder as a way to represent images. And then we trained the predictor in that representation space in an action condition manner, so that we have a world model of what a robot would do to the world by taking a particular action. Right? So we show the world to the system. This is a simulated robot. We take an action and run the simulator of your robot, and then observe the result, and then train the predictor to predict the representation of the result from the representation of the initial state and the action. Once you've done this, you can use this world model, which is action condition, to predict the outcome of a sequence of actions. You can put a objective for a task, which is essentially a distance in representation space between the predicted state and the target state that you want to reach. And then by optimization, look for an action sequence that actually accomplishes, fulfills the task. Let me skip ahead to the videos. So this works well compared to kind of other things people have tried on in sort of similar situation. Dreamer V3 is by Daniel Hafner and colleagues at DeepMind. TDMPC2 is another piece of work. But so there is a task, simple task like this consists in kind of by moving a little dot, like pushing a T-shaped object so that its position matches the target position. So what you see here is what actually occurs, and what you see here is what the system imagines will occur, after taking a certain number of actions. This is a more interesting one, but let me show you the full video. Okay, so this is a kind of robotic situation where this is kind of an initial state, and these are target states. And these are the plans that this Dino world model system using model predictive control plans so that the blue chips are being moved in such a way that they look as much as possible like the target. Okay, and there's a limited number of actions that the system can take. It's using what's called receding horizon planning, and that type of planning has been applied to a number of different situations with double pendulum and running through simple mazes and things like that. A similar idea was used by Amir Bar, who was a postdoc with me at FAIR. He is now a research scientist, and he's got some cool demos at this website. This is collaboration with people at Berkeley, as well as Kathy at NYU. And there, the type of training is that you get a picture from the cameras of a robot, and then the robot moves by a little bit. You know by how much it's moved and rotated because you get odometry from the wheels. And you get another frame, right? And can the system be trained to predict the representation of the new frame from the representation of the initial one and the transformation? And the answer is yes. And then once you train the system, you can tell it go to the blue trash can or something. So here it sees the trash can kind of far away, and here it's present. You can see it, but it's really far away. And it basically, through this imagination of what it's going to look like as it goes along, it can plan a trajectory to go to the trash can or whatever. And there's like a bunch of various demos that you can see on the website. This won the Best Paper Award, honorable mention at CVPR just a couple months ago. So this JEPA with distillation method was used not just in the context of Dino, but in context of learning representations for images as well as video, IJEPA and VJEPA. And it's really very much the same architecture as I showed before. Take an image, corrupt it by masking a big chunk of it, and then train, run those two images through encoders, and then train a predictor to predict basically the full representation from the partially masked representation. That system produces really good performance, and this is training time. It trains really fast. It produces good performance. This is for object recognition, top one on ImageNet. It works much better than MAE, which is another project that was taking place at FAIR, where the idea there was to train a denoising autoencoder. So you take an image, you corrupt it by masking parts of it, you train some huge neural net to reconstruct the full image. Okay, so it's a generative model. And it turns out it doesn't work linear as well. And it takes much longer to give you the wrong answer. So that was a pretty clear empirical demonstration that if you want to learn appropriate representations of high-dimensional continuous data like images, you do not want to train the system to reconstruct or predict at the pixel level. That's pretty clear evidence for that. And so JEPA is really kind of the way to go there. Video JEPA is a slightly more recent work, where you take a video, you corrupt it also by kind of masking a big chunk of it, and then train the encoder and predictor to predict the representation of the full video from the partially masked one. And then you can feed the representation here to a head that you train supervised to do things like action recognition or action prediction or whatever. And this system works really well. Certainly it's the best among all the self-supervised systems. There's a more recent, so there's an interesting point about this particular work, which is that, and this is very cool, if you show the system videos where something impossible, physically impossible occurs, its prediction error goes to the roof. So you show a video like the one here at the top where you have kind of a ball being thrown and kind of flying through the air, and then all of a sudden it disappears. It's not there anymore. So that violates object permanence. So you apply the VJEPA model over a sliding window of 16 frames. Its input is 16 frames long, right? So you slide the window over the video. And when it gets to that point, and it sees this empty frame, its prediction error goes to the roof. It says like, something strange happened here, basically. And so we've used that technique to test whether those systems, kind of like babies, testing them whether they were surprised by certain things that happen in video, and whether they have integrated basic notions of intuitive physics like inertia and solidity, gravity support, continuity, shape constancy, and stuff like that. This is a paper that it's on arXiv. We submitted it to the journal. And there's a new version of VJEPA called VJEPA 2 that just came out fairly recently, a few months ago, 3 months ago. And this one has 2 phases for training. One phase, which is the same as VJEPA 1, except on more data and bigger. And a second phase, which is action conditions. So there, it's kind of like this world model where we freeze the encoder, and then we train a predictor, which is action condition on robotics video, and then we can use it for planning. And this works really well for planning. There's various demos you can see at this website. This is the set of training data that was used. This, by the way, corresponds to, we're still far from the efficiency of humans and animals. The amount of video that we use here corresponds to about a century of video, right? And a 2-year-old understands the world better than this thing. So, we still have some work to do, but it's pretty cool. Let me show you a demo of planning. So this is using the one model on top of the encoder. You start from this configuration. You want to get to that configuration, and you have some distance in representation space, and the system searches for a sequence of actions that will basically produce in representation space something that corresponds to this, and like manipulating an object. Now, the cool thing about this is that it's never seen this particular robot before. And it's very robust to the particular anatomy of the robot, to the position of the camera. It's pretty interesting. I'm going to skip the details of how this is trained precisely, but it's internally the prediction of the representation space is trained autoregressively, a little bit like an LLM, except it's done in continuous representation space, not in token space. These are performance on various tasks, which I'm not going to bore you with. Okay, but what we really want to is train those JEPA architecture end-to-end using those regularized methods that we think we understand better than the distillation method. So we have a number of such methods. We proposed a few, Barlow twins and VC regularization, and then other people like Hima at Berkeley has proposed MCR squared. Some of our colleagues at NYU have proposed another method called MCR. There's WMSE. Like those methods are basically different ways of ensuring that the information coming out of the encoder is as informative as possible. Okay. So try to maximize the information that comes out of this. Now there is an issue with this, which is that to maximize a quantity, it's nice to be able to compute it. But if you can't compute it, have a lower bound on it. Okay, so you can push up the lower bound, and then the quantity you want to maximize goes up. Unfortunately, for information, we only have upper bounds. And so what we do is that we use a criterion that is an estimate, an overestimation of the information coming out of the encoder, and we maximize that, and we cross our fingers. And it works. Sort of. The basic idea of all that, I mean, you can think of the idea of maximizing information as making sure that the vectors that represent the inputs basically fill up the space, right? They make use of the representation space. So that leads me to this little thing. So imagine that this is a matrix of a bunch of samples that are run through the encoder, okay? Each row is a different sample. Each column is a different variable of the representation vector. And what you want is this matrix to be informative. So you don't want it to be constant, okay? You don't want it to be too singular, low rank, you know, whatever. And you have basically two ways of making sure it's kind of informative. One is you make sure all of the rows are different. Okay, so basically every sample will get a different representation, right? And you can do this with contrastive method by pushing all the rows away from each other. The alternative, which is a particular way of implementing regularized method, is to make the columns as different from each other as possible. And what that does is that it makes sure that every variable of the representation is individually informative and uncorrelated from the other variables. So uncorrelated doesn't mean independent, and this is why we're not maximizing a lower bound on information content, but an upper bound. We're ignoring dependencies. But basically, in this case, what you want is you want to make this matrix multiplied by its transpose basically equal to identity. So that will make the rows orthogonal to each other. In this case, you want to make this matrix transpose times itself as close to the identity as possible. And that's basically making all the variables uncorrelated. In fact, those two problems are dual of each other, and we have a paper on this. Because what matters are the singular values of this matrix, and it doesn't matter whether you compute the graph matrix or the covariance matrix. But anyway, so this kind of is understood and works pretty well, and there's this method called VC regularization that I'm not going to bore you with details, but you can train world models with this. So you can take a relatively simple encoder on, you know, input images or videos, sequences of frames, and then train a predictor which is action conditioned. And this could be a simulated environment. And once you have this, you can again do planning by optimizing a sequence of actions to kind of minimize a particular objective. And you can use this to kind of plan trajectories in mazes. Unfortunately, this is not playing for some reason. It's supposed to be a video. And it works, you know, pretty well. I mean, we still have a lot of work to do there. Okay, so this is essentially the last slide. I'm recommending, if you are interested in like pushing AI to the next level, going beyond what LLMs can do, having AI systems that understand the physical world, have persistent memory perhaps, can plan, can reason in the way, you know, through optimization, the way I described it, then you need to essentially abandon generative models in favor of those joint embedding architecture, the JEPAs. Okay, I'm not being very popular in the LLM world. Okay, I have to get bodyguards when I, you know, walk around Silicon Valley. abandon probabilistic models in favor of those energy-based models because, probabilistic modeling in this case is intractable. Abandon contrastive methods in favor of those regularized methods. And there's still a lot of theoretical work to do there and practical work as well, and objective functions to figure out like how to do that best. I've been saying for 10 years, minimize the use of reinforcement learning because it's so inefficient in terms of number of trials. In some cases you don't have any choice, you have to use it, but it's so expensive in terms of number of trials that you want to minimize its rule, its use, and this is not by itself going to lead us to human level AI. This is a hypothesis that, for example, DeepMind started out with. When they were founded, they thought that they were going to get to AGI or whatever you mean by that through reinforcement learning. That turned out to be a complete failure. Not complete because good things came out, out of this effort, but like AlphaGo. But this is not a path to human level intelligence by itself. So bottom line is, if you're really interested in human level AI, don't work on LLMs. Thank you very much. So I'm not running the show, so I'm not sure if we have time for questions, or if someone should designate the questions.
I have a question. So when do you predict the ChatGPT moment will come for the robots? Because robots are really help human being free from those daily labor work. Yeah, everyone is kind of anticipating that, but when that will happen?
Yeah, that's a $60 billion or 600 billion, I don't know, dollar question. When will we know that we're on a good path, so that we'll have AI systems that have the proper architecture and capabilities for robots to be useful? Okay, so first of all, you have to realize there's a lot of companies nowadays building robots, right? Humanoid robots and stuff like that. And you see those amazing demos on the web of those things, kind of doing pretty impressive feats. That said, none of those companies, absolutely none of those companies, has any idea how to make those robots smart enough to be useful. Okay, there's an enormous amount of investment riding on a bet that AI is going to make sufficient progress so that by the time those robots are commercially viable in terms of hardware, AI will have made sufficient progress to make them useful. Okay, there may be a small number of very narrow niche applications where those robots would be useful without actually kind of having systems of the type that we talked about. But the number of such applications would be very, very small. And the idea somehow that all of a sudden, all human workers will be replaced by robots is stupid, crazy, nuts. It will happen. It will take time. There's not going to be an event, it's not going to be a day before which we can say we don't have human level AI, and after which we can say we do. It's not going to be an event. There's going to be like a lot of different breakthroughs that are necessary, and progress and engineering to make those things work, and to kind of scale them up, and various techniques and blah, blah, blah. So it's going to take a while. It's going to be continuous. But my guess is that, within 3 to 5 years, we'll know if we're on a good path towards systems that have the capabilities that we need, to reach human level AI. Now, I think it's probably much harder than we think, because it's always harder than we think. And historically, over the course of the last 7 decades of AI, everyone, including pioneers of AI, have consistently overestimated the capabilities of whatever technique they were interested in at the time. One of the first AI system produced by Alan Newell and Herbert Simon at the CMU in 1956, I think, was called 1957, was called the General Problem Solver, right? Very modest. And what they say was, it's not stupid. I mean, they're Turing Award winners, right? Pioneers of AI. What they say is that, solving a problem is, you specify a space of possible hypotheses or solutions, and then you have a function that tells you whether a particular solution solves your problem or gives it a score, like the length of a route between cities, for example, right? And so then intelligence is just a matter of searching through that space of solution for the one that, maximally fits the bill, minimizes the cost function, okay? And so they wrote a program that does this, now the problem is just to kind of specify the search procedure and, specify the characterization of the solution. Now it turns out this was before computational complexity was invented. Like almost all interesting problems are exponential, or NP-complete or NP-hard, or, one of those. And so that was not a solution, but they thought it was a general problem solver. So there's like, repeated, then, a year later, the perceptron was built, one of the, first learning machine, an analog computer. And people thought, you could expand the perceptron and train it, to eventually have systems, intelligent robots that would be able to perceive and everything. It turned out to be a lot harder than they thought. It turned out to take 20 or 30 years for backprop and material neural nets to come to the fore, and then another 15, 20 years for them to actually become popular. Right? Those techniques did not become popular until the early 2010s. So yeah.
Then I'm curious. First off, thank you so much for your lecture. It was amazing. I wanted to ask, so there's scientists in Switzerland specifically who are working on biological computation, and I just wanted to get your take on that.
There's a lot of people actually around the world. Yeah, Switzerland has been a kind of particularly hot point there of people trying to either simulate kind of large nervous system, but neural nets, but realistic neural nets, with the idea somehow that if you make the simulation accurate enough, intelligence will emerge from it. It was in fact a huge European-funded project called the Human Brain Project to just do that. That was a complete and utter failure. Many of us said that in advance that this would never work. I mean, it's basically cargo-cult science. It's like, you're reproducing all the details of something you observe in biology without actually understanding the underlying structure, and you hope that somehow you will have the appropriate characteristics. I mean, that's just that's nuts. It's like, it's like you copy birds and you have them, flap their wings and they have feathers and everything, and you hope that they're going to fly. No, I mean, you need to like study aerodynamics and stability and understand the underlying principles, right? So this didn't work. Now there is another set of work, which maybe is what you're referring to, which actually originated many years ago in the 1980s at Caltech, with Carvey, which was the idea that we should basically implement electronic circuits that are analog and subthreshold and low power, low current, so that we can sort of basically simulate neural nets, but with electronics, silicon electronics. There was a lot of hope in the 80s about this, and there were a few companies, including the one I worked for at the time, AT&T Bell Labs, that built analog chips to implement neural nets. It never amounted to much, because it turns out electronics is both too big and too fast for that. There's a big issue, which is that to implement a synapse, or the equivalent of a synapse, right? You need to be able to do a multiplication between the input signal and that kind of coefficient of the weight, right? This is the way all neural nets essentially work. So you have to have a multiplier. You can either implement it in digital or in analog or in some sort of mixed hybrid thing. But in the end, it's going to be pretty big on your chip. And so there's a limited number of those that you can put in. Okay, the typical GPU has several thousands, but there's a limited number of those you can put on the chip. And the number you can put on the chip is not large enough that you can have one physical multiplier per synapse in your neural net. And so what you have to do is basically reuse the same piece of hardware for multiple parts of your neural net. You have to do hardware multiplexing. And what that means is you have to shuffle data from memory to that, to this, computing infrastructure, basically, right? That is what costs energy. All the power that is consumed in GPU, the main reason they are much less efficient than neurons is first because they are much faster, but the second because you have to fetch data from memory, and charging a big wire takes a huge amount of energy. So we're not going to solve that problem unless we have a new fabrication technology that is much smaller and so on. Okay. The rest, yeah.
Okay. Hi, thank you so much for coming. I have some questions about the prediction on education in the upcoming decade or so. So we're seeing a lot of change in how we gather and track information nowadays. If you were advising, let's say, a youth or someone in their 18 or 20-year-old, what type of discipline would you think is really useful in the next coming decade? And would you anticipate some of the prerequisite lessons that we've been accustomed to disappear? Let's say coding, foundational math, so on. Thank you.
I still think learning basic techniques in science and engineering is the thing you should do. It's not because it gives you some intuition, mental model, etc. Maybe the low-level mechanics of how you compute an integral will be done by a computer, so we know the case, or how you solve a differential equation, or how you write code, right? All of this will be taken care of by assistants, essentially. So people will be working at a slightly higher level, but it's kind of like you'll be. It's like every student will be in the same situation as a professor working with students, except the student will be working with AI systems that will be playing the same role as essentially a student for professors. Because the truth is that it is students who teach the PhD advisors, not the other way around. So I think it's I don't think it's going to change much. But if you are, I wouldn't study like pure computer science. I would study something a little more fundamental, like engineering, let's say electrical engineering, or physics, or applied math, because that's where you learn the basic techniques that have a long shelf life, that basically subtend pretty much everything we do in technology and science for that matter. And then the mechanics of it will be done by assistant, AI assistants. That's fine. So if you had a choice between taking a course in, I don't know, mobile application programming and quantum mechanics, take quantum mechanics.
Those are beautiful pictures. They make me come up with this question. Do you think your water model can solve the three-body problem? And if possible, what kind of training data you would need?
Well, it depends what you mean by solve. I mean, to some extent, we already solved the three-body problem. We know the differential equation, we can just integrate them, right? So I mean, we can compute the trajectories of three-body in the orbit around each other. There's even some recent results that show like all the numbers of stable orbits of three objects, around each other. Most of them are chaotic, but a few of them are actually kind of chaotic. So, so what do you mean by solve? You mean analytically solved? I mean, maybe there is no analytical solution. So why will it be solved?
So if you don't use any mathematical model, just train the work model.
It will probably learn if you give it x, y position and velocities and probably masses, right? With a bunch of bodies kind of crawling around each other, it would probably figure out Newton's law. I mean, your world model would be like state of the world at time t. Can you predict the state of the world at time t plus delta t? It will learn that differential equation. And by the way, those pictures I took. I took them in my backyard in New Jersey. The skies are terrible in New Jersey, but it was good enough for those pictures.
Thank you very much for your talk, Ryan. I just wanted to mention, so you mentioned the work of Fernando before, and the question there was to say how can we make machine learning like babies, and they seem to learn different things at different age. And then you're mentioning this second idea of hierarchical learning or hierarchical intelligence. And so the question is, do you think that we should give machine different amount of different type of data at different stages, a bit like the second version of JEPA V2? Or do you think it should also be at the architectural level? And like, do you think that the baby brain, human brain, is actually made in such a way that when it's looking at all this data, it's filtering it to learn these different things at these different stages?
Okay, I think the way to deal with the hierarchy is that what defines a high level in hierarchy is the fact that you can make predictions that are longer term. Okay, so if you build the architecture in such a way that you know, at one level the system is asked to make a long-term prediction, it's going to have to learn an abstract representation of the input that allows it to make those predictions, right? And so the way to build hierarchies, abstraction hierarchies, is forcing the system to make longer-term prediction. Now, how does the brain do it? I have no idea, but clearly humans have a way of elaborating abstract representations that is, you know, strictly more powerful than most animals, at least most humans.
Great. Again, thank you for the speech today. I was wondering if you could reflect a bit more on what your advice would be for specifically, let's say, graduate students starting their career and interested in AI, and where do you think the best learning environments currently are? If you can be as unbiased as possible, would it be, would you advise people to stay in academia and stick to universities, or going to large companies, or would you say that there is a significant momentum of innovation in Silicon Valley as well, and if the barrier to entry are not too high right now?
Okay, my answer is going to get me in trouble. So first of all, if you're really interested in research, there is nothing like doing a PhD. And so if you just directly go to industry and you think you're going to do research, you know, first of all, because there are fewer and fewer places where you can actually do research in industry these days. And the thing that's going to get me in trouble is that you don't want to be in Silicon Valley at the moment, because there's kind of a bit of a herd effect and kind of a local cult where like everybody kind of works on the same thing and try to copy each other. And that's just not, it's not the way, you know, creative people should work. So stay away from Silicon Valley, at least for a while, until you have, you know, a good idea what you want to do. So I think we found a sweet spot at Fair Paris. So it turns out in France there is something that has been around for about 40 years now, that allows PhD students to do their PhD in residence in industry. And at Fair Paris is about maybe 100, 120 people. All those 120 people is 40 resident PhD students. And a PhD in France is 3 years, like in most of Europe. So you're basically churning out 12 students, 12 PhD students per year. It's contributing to the local ecosystem, which is probably one reason why Paris is kind of the hotbed of AI startups at the moment in Europe. And it's a best of both worlds, because those students, you know, are in an environment where there's a lot of engineering support, there's a lot of GPU access. They are in a community with other students working on kind of similar things where they can talk to the best experts in the world, who may be their advisor within the company, but they also have an academic advisor, and they can do as much time in the academic department as they want. So it's the best of both worlds. We've been actually trying to reproduce this in the US with bilateral agreements with various universities wherever there is a lab. With some success, but it's not as systematic. So yeah, I mean, there is good. I have a foot in both, right? I kept the foot in academia as well as industry. I think those two worlds are complementary. I think most of the good creative ideas come from academia still, and they take 3, 5, 10 years sometimes to make it to, for people in the industry to realize they are good ideas, to pick them up. So yeah, I mean, I hope I'm answering your question.
Thank you.
I have a question about the world model, because you were talking about perception and then coming to the representation of the state of the world. I'm just curious in what way you account for the perception to be subjective. No, I mean it's subjective, because obviously we all see colors, but what they really are in our eyes with the cells and who we are as humans. I mean, all of our perception is different. Like we're all made up with different hormones and body types and memory, as you mentioned, but then also just our, philosophically speaking, our talents and our, yes, everything that we're born with, so to say, that comes into existence. So I'm just curious about this model.
Yeah, I mean, clearly there is no single way of defining optimal representation, right, for the system. There's many different ways to encode images in such a way that particular type of informations are preserved and others are eliminated. And for example, we all have some sense of the texture of the carpet here. That does not preserve all the details about the carpet. But we have some representation relatively low level as to what it represents. We're not all subject to the same type of illusions. We don't have all the same characteristics as to what is easy for us. I don't know about you, but I think it's very common to a lot of people, couples in particular, where I would open a drawer and look for some thing for the kitchen and look at it, not find it, and ask my wife if she comes and boom, right? She sees it right away. People are very different in that way. It's actually a bit of a gender difference also in that respect. Not clear there was some evolutionary argument for this, but so that's probably because our perceptual system are wired slightly differently for different people. What we call dyslexia is probably a way that our visual systems are wired that give us an advantage for other tasks than reading, right? The reason why it's relatively prevalent among humans, and reading has only become useful in the last 2,000 years. So, so I think there was a question which was before work like and stuff like that, whether self-supervised learning would work, because how do you characterize good representations of images? If you don't know in advance, what are you going to use it for? And I was in that camp early on, where I didn't believe unsupervised self-supervised learning would ever work, because there is no kind of good way to characterize a good criterion to train them to characterize good representations. And a computer teacher joined mine about 20 years ago about this, and we have to accept the fact now that there are good generic representations of images that can be used for almost anything we can think of. There's probably a lot of tasks that those systems cannot do, but they don't seem to be things that we're interested in solving. I'm going to keep going until you stop me, so I don't know how long did it. All right.
Yeah. As in the beginning, you just mentioned that for example, the child, we don't need to tell them too much and they can learn something. But I think now in the world model, and we have some limitations, but now all the models actually is the data driven model. We spend a lot of time to collect data or clean data. But my question is that in the next decades, so should we to move to the model driven, should we to involve more physical principles or something like that? It's like a human being when we go high school, and they will have some principles to help us to learn some high level models.
Yeah, this is for like very, very high in the abstraction, ladder. What we're talking about here is the type of abstractions and understanding of the physical world that a cat can have. A cat has an extremely good understanding of its own physics, right? Or the physics of its interaction with the environment, right? You see a cat kind of wanting to jump on a piece of furniture and kind of looking at the bottom and sort of planning a jump and doing bounce or something. Bounce, and you don't realize how they've done it, and they figured out all the frictions and everything. I mean, they have an extremely good model of their hands. It's this type of learning that we're talking about. Now, much higher up in the hierarchy, there is the notion of formal physics and stuff like that, but that's way not learning.
Sorry, probably this is the last question because Dr. LeCun will have other event later.
I'll give you a little bit of that.
So let's thank Dr. LeCun. One, we can come out here and take a group photo with Dr. LeCun for future kids to watch.
Good question. Just working on neural nets and 3D scene understanding. How would you compare it to energy-based models? Like, do you think it's gonna video frames gonna converge into like?
I mean, it's orthogonal. You can use the energy-based models basically encompass pretty much everything people do. So I mean, models that people work on. So it's not incompatible.
Thank you so much for an amazing lecture. And like I'm also working in AI like